ये नीचे में
मैंने शेयर किया है स्लाइड्स। कैन यू सी इट?
yes ma'am, we can see
ओके।
ये दूसरा देखो आगे देखो इससे पहले हाँ,
ये मैं आगे पीछे कर रही हूँ, आ रही है नजर आपको?
stop मैडम हम थोड़ा सा इंट्रो करवाएंगे, उसके बाद फिर आपको इनवाइट करेंगे तो
अच्छा, नहीं वैसे मैं कह रही हूँ आपको मेरी
जी
स्लाइड्स जो है वो स्क्रॉल होती हुई
जी
नजर आ रही हैं।
जी 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 मैडम, आपके स्लाइड्स में
अच्छा
क्लियर
बस,
नजर आ रही
ठीक है ठीक है।
है। अभी स्टॉप करना होगा। आप आप शेयरिंग थोड़ा स्टॉप कर सकेंगे मैडम?
जी एक मिनट करती हूँ। स्टॉप हो गई या अभी नहीं हुआ अभी?
मैडम को हमारी नजर आ रही है? मैडम हमारी स्लाइड्स आपको नजर आ रही है?
एक सेकेंड। जी जी, यूनेस्को चेयर, यस नजर आ रही है।
शुक्रिया। इसके साथ बिस्मिल्लाहिर्रहमानिर्रहीम। आवाज आ रही है आपको? एक मिनट। Bismillahirrahmanirrahim. It gives immense pleasure to welcome you all to the UNESCO Chair lecture series of UNESCO Chair in Medicinal and Bioorganic Natural Product Chemistry. This is a regular feature of the UNESCO Chair here at iccbs. Actually, UNESCO Chair Network is a global initiative of UNESCO established in 1992, linking universities and research institutions to advance knowledge, training, and collaboration in science, education, culture, and sustainable development. Today, it includes more than 1,000 chairs and 45 networks, serving as a think tank and bridge builders between the academia, civil society, and policy makers. UNESCO Chair program actually promotes internet, international inter-university cooperation and networking to enhance institutional capacity through knowledge sharing and collaborative work. The program supports the establishment of UNESCO chair networks in key priority areas related to the UNESCO field of competence. Today, 170 of the UNESCO chairs included in the UNESCO chair program are related to the natural sciences. UNESCO chair on medicinal and bioorganic natural product chemistry is a UNESCO chair established in ICCBS, and ICCBS is a distinguished center of University of Karachi, which provide cross-disciplinary leadership in a vital scientific fields under the guidance and advocacy of Professor Dr. Muhammad Razasha. This year was established in 2020, and now it is running its second tenure, and the incumbent UNESCO chair holder is Professor Dr. Muhammad Razasha. The objectives of the UNESCO chair in medicinal and bioorganic natural product chemistry are within the broader range of the UNESCO chairs network. We aim to promote research and training. We want to promote inter-university networking and also linking researchers and practitioners within our country. So today Our presenter is Professor Dr. Humaira Masood Siddiqi. She is a professor of chemistry at Qaid University, Islamabad, and leading figure in Pakistan scientific landscape within more than 70 years of teaching and research experience in organic and polymer chemistry, earning a PhD from National Institute of Applied Science of Lille, France. She has built a strong research portfolio centered on the synthesis and characterization of liquid crystal molecules, polymers, and their composition, and their composite materials. This include epoxy, amine-based hybrid nanocomposites, polyamides, biodegradable composites, and polymer dispersed liquid crystals. She earned numerous distinctions throughout her career and secured multiple competitive research grants from diverse funding agencies, serving as a principal and co-principal investigator. As HEC approved supervisor, she has mentored more than 59 MPhil and 18 PhD students, authored 150 research articles within academic records exceeding 20,000 citation and H-index of 24 and I-index of 55 alongside multiple national and international fellowships. She also served on several departmental committees within QAU Department of Chemistry. Now I invite Professor Humaira Masood Siddiqui to deliver his talk on polyamides as a functional materials towards the sustainable developmental goals. Thank you. Welcome, madam.
Thank you, Dr. Khalid, for introducing me. Can you see my slides?
Yes.
Okay.
Yes, ma'am. You will.
Right.
Okay.
Can you see?
Yes, ma'am.
Okay. So, Bismillahirrahmanirrahim. First of all, thank you, Dr. Khalid Khan, for inviting me to talk about my research group's work, and Professor Dr. Raza Shah Sahab for inviting me to deliver this plenary lecture. So the talk is about the polyamides as functional materials towards sustainable development goals. I am serving in the Department of Chemistry, Qaid University, Islamabad since 1999. And as you have introduced me well before, so I will go to the main topics. So contents of the presentation will be some introduction about the sustainability, sustainable development goals, polyamides, its applications for optoelectronics and in the optical sensors. Sustainable Development Goals. In 2015, the United Nations member states adopted the Sustainable Development Goals (SDGs) with the aim of creating a more just, sustainable, and peaceful world by 2030. So there are 17 Sustainable Development Goals. One is no poverty, second is zero hunger, third is good health and well-being, fourth is quality education, fifth is gender equality, sixth is clean water and sanitation, seventh is affordable and clean energy, then eighth is decent work and economic growth, ninth is industry, innovation and infrastructure, 10th is reduced inequalities, 11th is sustainable cities and communities, 12th is responsible consumption and production, 13th is climate action, and 14 is life below water. 15 is life on land, 16 is peace, justice, and strong institutions, and 17 is partnerships for the goals. So my lecture will encompass the sixth Sustainable Development Goal and a little about the seventh one also, the clean water and affordable and clean energy. Heavy metal contamination. So heavy metal contamination in water has been an issue to the environment and human health. The heavy metals bioaccumulate, they are non-degradable, So you can see industries, mining, agriculture, and urban units, they charge their pollutants in water, and the life below water is contaminated or polluted with heavy metals or other organic pollutants. And the problem is that they accumulate and they are non-degradable. The harmful effects caused by the heavy metals, so the toxic heavy metals are mercury too. This spreads diseases, different diseases like cancer. The permissible limit in water for mercury 2 is 2 parts per billion. Lead 2 affects the liver, kidney, central nervous system, and gastrointestinal tract, causes hypertension, infertility, arthralgia, and coma. Its permissible limit is 0.05 ppm in water. Copper 2, it causes headache, depression, and learning problems with permissible limit is 1.3 ppm. Cadmium 2, it causes renal dysfunctions, pulmonary problems, bone tumors, high blood pressure, and bone deformities in fetus. Arsenic 5 causes pigmentation changes, nausea, and cancer of liver, skin, lungs, bladder, and kidney, and its permissible limit is 0.01 ppm in water. So the detection and removal of all these toxic heavy metals is necessary. So you have to constantly monitor the environment for these pollutants, and the water contaminants should be treated before the water is used as potable water. The common adsorbents for heavy metal ions. So heavy metal ions can be separated from metals by using some adsorbents. There are natural and synthetic adsorbents used for the removal of heavy metal ions from water. So they are activated carbons, zeolites, clay materials containing metal oxides, magnetic particles, clay minerals, ion exchange resins, catosanes, polymers as ion exchange resins, and chelating resins, etc. Among polymers, we hear a lot about the hydrogels these days. This is the structure of hydrogel. It has a porous structure in dry state. It can absorb 100% water when water is added to this dry gel. So this is one of the example: chitosan, polyvinyl acrylate, and polyvinyl pyrrolidone. So under the action of microwave radiation, the contaminants, they are adsorbed onto the surface of these hydrogels or into the micro or nano pores present in the hydrogels. The challenges of using these type of materials is sometimes they are not selective. There is a problem of regeneration. You have to maintain and monitor them constantly, and they cannot be used sometimes under extreme wastewater environments, such as high temperature and chemical corrosion. So you need a robust material which can be used to detect and then separate these heavy metals. Polymers. Polymers, these are polymers. So the history of polyamides dates back to 1908 when the first polyamide was synthesized by Howard and Renshaw. So these polymers are the actually organic molecules, but they are very long chain molecules. So one monomer is repeated many times over itself to form a polymer, a long chain molecule. And polyamides, they contain imide in a form of the tetracyclic ring. This is the imide structure where the nitrogen is flanked to two amide moieties. So all our organic chemists, they know very well which is the what is the structure of amides. To form the polyimide, we need a dianhydride, we need a diamine. These are polycondensed under thermal or chemical polymerizations. They are imidized, two steps, and they form the polyimides. So this is one of the diamine, oxydiamine, and here R is the structure of dianhydride. Various structures can be used. So this is a simple reaction, nucleophilic reaction. AB is attacking the anhydride linkages and producing the imide linkage. Polyimides have versatile applications. The specific properties of polyimides vary depending upon the formulation, including the choice of monomers and the processing methods. Using a wide range of different dianhydrides and diamines, you can play and form various materials. Some of the examples of polyimides being used in polymer electrolyte fuel cells. This is a vehicle which is using these fuel cells for its battery systems, and they are tested built in fiber optics. So polymers are also used as fiber optics. The colorless polyimide films, they can be used as touch panels, printing circuit boards, in the devices for displays. So you see the curved structure. So these are the panels or screens with curved structures. You might have seen the mobiles nowadays, which can be folded. And also for the printing of solar cells, polyimides are also used. And this is a bright structure when polyimide coating is used with liquid crystals as sensors. So for the optical sensors also we use the polyimides. So this area is optoelectronics, this is optical sensors, and these are for the energy applications. And this is for the signaling and transfer of data, so fiber optics. So a lot of versatility of polyimides due to the change of the structure of diamides and dihydrides. We have, so optoelectronics, they use the relationship between optics and electronics, that is the light and energy. Optoelectronics include the design and production of hardware devices that convert electrical energy into light and light into energy. So you see the Intel cores, you see the optic devices, LEDs, both of these constitute optoelectronics. Likewise, the flat panel displays, the solar cells, and other accessories. So this is an example of one of the works which we had done in our laboratory using an oxydiamine and a diamine, which was synthesized in our laboratory. So this is a TPA linkage which is condensed with carbozoles to form the polyimic acid, and then the thermal ionization giving you the polyimides. So these are the electrochemical testing, electrochemistry CV curves, the UV absorptions. So you can see they are active in this range of 200 to 400, and their optical responses and the use in the electro-optics. This is another work where we have used the methylene diamine and the same carbazole containing the triphenylamine with the dianhydride, different dianhydrides forming the copolymer to produce different types of polyimides. Another work in which we use the benzoxazole formation. So benzoxazole was synthesized using 2-phenol at 4 millimeters. So you can see it PPA 200, and then we form its triphenylamine using CC fluoride and fluoronitrophenol, and then reducing the dihydrogen into the NH2 compound. So a diamine is again formed containing these aromatic groups. So these were also condensed with different dianhydrides, forming the copolymers with various dianhydrides. Their optical responses in these and their electrochemistry, which showed that they are good optoelectronic materials. So this was one of the work which was published in High Performance Polymers. Very briefly, I have talked about these optoelectronic materials which we have made using polyamides. Now the particular example of liquid crystal-based optical sensors, so using polyamides. Optical sensors. These are ideal for applications requiring real-time, non-destructive, and cost-effective analysis. Liquid crystal sensors offer several important advantages. This is a table which shows the key reasons why liquid crystal sensors are important. They are highly sensitive, can detect small changes in the environment. Versatility, they are customizable for various applications. Real-time monitoring, continuous and dynamic data can be obtained in real time. Non-destructive, they are a non-destructive technique. Repeated testing without sample alteration can be done. Selectivity, they are highly specific for target analytes. So you can design your materials to form the sensor to target a particular foreign body or analyte which you want to detect. Lower power consumptions, they are energy efficient options, cost effective, they are economically sensing solutions, rapid response, they are quickly analyzable, and you can make decisions very rapidly. And there is minimal waste production, so they are environmental friendly. They have wide application in diverse fields and sensing needs. Now, what happens in the optical sensors? Liquid crystals, they are small molecules which align in one direction, right? So liquid crystal is a state between the liquids and the crystal. So there are certain organic molecules which can show you a mesophase in between the liquids and the solids. Okay, so liquid may you have no orientation of molecules. In solid, you have perfect arrangement of molecules, while in the mesophase or the intermediate liquid crystal phase, you have some of the molecules, their alignment in some directions, not in others. So when the liquid crystals are aligned vertically, so these are small organic molecules which are aligned in one direction vertically. So this type of arrangement is called the homeotropic region. When light passes through it and under the crossed polarized microscope, you will see nothing. This will be the dark image. However, if you add some foreign substance, it will damage this arrangement of the liquid crystal molecule. So when they will be dispersed in different directions, now light entering into it will see different angles for the transmission. So differently, so they will have different refractive indexes due to the arrangement of different molecules. This is called the anisotropic state. So this will be appearing under the microscope as a birefringent texture. So this type of a flowy texture with the bright thread-like images, just like forms with these black areas in between them will be observed under the crossed polarized microscope. Right. So these two states under cross polarized microscopes, they form the basis of detection for the optical sensors using liquid crystals. These are the fundamental principles of crystal-based optical sensors. तो इसका मतलब है कि when there is nothing, कोई चीज इनके साथ इंटरेक्ट नहीं कर रही, right? In that case, liquid crystal will not perturb, will not be perturbed, so no light will be passing through it. But when there will be something which disrupts the arrangement of the liquid crystal, you will observe something, some bright texture due to the liquid crystal's disorientations. So, liquid crystal-based detections, they are now being used as for gas sensors in the nitric oxide to detect nitric oxide molecules, ammonia gas molecules, for the biomolecules such as protein and DNA, and for the detection of heavy metals such as mercury, cadmium, lead, and chromium 3 ions, and for the detection of viruses and bacteria too. So these are some of the applications of liquid crystal-based detection. What are the components of liquid crystal-based sensors? First thing is you need a substrate. A cleaned glass slide is used as a substrate. So the substrate is a glass slide you normally use for the biological specimens to see under the microscope. Second is alignment layer, a layer that will align the liquid crystal molecules in a specific orientation. The commonly used substance is DMOAP, dimethyl octadecyl 3-trimethoxysilane propyl ammonium chloride. So you see, this is a long chain molecule with the silicon oxide moiety here and ammonium moiety here and a long hydrophobic chain. Now this molecule has three parts: the reactive anchoring part, the trimethoxysilane group. These are the hydrolyzable groups. So in the presence of the moisture, they can form silanol groups, which can undergo condensation to form a durable cross-link siloxane networks. The covalently anchors the molecules to hydroxyl rich substrates like glass, silica, and metal oxide. So on glass, if they are hydrolyzed, the glass has OH, so they will be joined here with the glass substrate. Okay? So this is hydrolyzable. The second is the propyl chain spacer. So this is separated by a 3-chain separator, which is necessary for the flexibility of the reactive head. So this is the reactive head, which will be oriented itself. It will orient itself, and then it will also align the crystal molecule. So it will bond effectively to surfaces without staining. The third part is active tail, quaternary ammonium and octadecyl chain. This ketinic group features two methyl groups and a long C18 hydrophobic hydrocarbon chain in liquid crystal devices. The octadecyl chain is responsible for aligning the liquid crystal molecules uniformly for neutron. So this is after hydrolysis. On the glass substrate, this has been attached. So this is the DO coated slide. Third part is the liquid crystal material, the main sensitivity. So there are various liquid crystal materials available in the market, and this is one of them. It is 4-cyano 4' penta biphenyl, commonly used liquid crystal material and liquid sensor. So you see, there's a biphenyl with a long chain, 5 carbon chain, and a cyano group. You see the dipoles. So this part is hydrophobic, this part is aryl group, and this is the highly polarized molecules, polarized group. Okay? So this is a polarized part, hydrophobic part, aryl part, and polarizable part. This is the main constitution of a molecule which can form liquid crystal phases. Why this is selected? Because it shows you the liquid crystal transition at room temperature. So its transition, its temperature where it shows you the liquid crystal state is at room temperature. Okay, so from room temperature to 40-50 degrees. The fourth one is the sensing interface. So actually this is the place where the sensing is performed. So this recognition layer enhances the sensor selectivity and sensitivity. So these things are important for sensor, and this layer it plays a vital role in the selectivity and sensitivity of sensor. Based on the sensing interfaces, liquid crystal sensors can be classified into three categories: liquid crystal solid interface, liquid crystal aqueous interface, and liquid crystal droplet interface. So in all the three, there is a difference. So here you have a solid interface between the liquid crystal and solids. Here you have an aqueous interface between the liquid crystal. So aqueous phase and surfactants, they are present with the liquid crystal with a grid. And in this case, a droplet interface is formed which aligns the liquid crystal. So the work I am showing you is the second one, the liquid crystal aqueous interface. So in the liquid crystal aqueous interface, transmission electron microscopic grids are used in surfactant or an amphiphilic molecules. So this will be the constitution of the liquid crystal interface. You need the liquid crystal, you need an amphiphilic molecule, and at its interface you will add your analyte and it will be detected. Fifth part or component is the signal processing unit. For various applications, these are various, so that this is the optical sensor, so we are using the polarized optical microscope. And generally, the lens width and time rate is used to observe the optical response of the liquid crystal. Now, what is the difference between our work and the conventional methods? So, for the conventional liquid crystal sensor, as I told you, that the glass slide is coated with the DMOAP, and this is the coated glass slide that we have the liquid crystal, and there is a lighting layer of this molecule aligns the other liquid crystal molecules. So we put a time grid and then you add the analyte. What we have attempted is we replaced this DMOAP with a polyamide which contains appended alkyl groups. So we are actually doing the same thing, but the difference is that we are using a polyamide, a plastic or the glass slide. This is the simple coating. It can wear off from the glass slide. But this polyamide coated glass slide is resistant as compared to this one, so we can reuse it. The other thing is same, we use the liquid crystal. We put the depth grid and then we apply the analyte solution. So the aim and objectives of this was to fabricate the polyamide-based simple real-time selective and sensitive liquid crystal sensor to detect the metallites in water. The synthesis and characterization of polyamide containing a normal fermented group, synthesis of amphiphilic thiocyanate ligands, selectivity of liquid crystal-based sensor for mercury ions. The first part of the synthesis, visible property of amphiphilic ligands for mercury ions. As we are targeting the mercury ions, so we are going to synthesize the amphiphilic ligands which can selectively attach with the mercury ions. So we took two bromides. So you see this is C12 chain bromide. So C12H25Br. And in one scheme we use a simple hydroxy benzaldehyde for oxybenzaldehyde. In the other we used another carbonyl in the acytic molecule. So this is O alkylation, and here also this is N alkylation. Then we use this thiocyanate carbazole to form the derivatives have a Masood derivative of this aldehyde and this cetane. So you see one of the carbonyl of the cetane forms this, we will N with this molecule. Why thiourea is used, thio or sulfur is used because mercury guys, they have a very good affinity towards the sulfur. So that is why we are designing our electrophilic ligands for the detection of mercury guys. These two electrophilic molecules have been reported otherwise. So this was the reported one. See what we have done it. Second was the synthesis or the designing of the monomer. So now we are going to design that. The amine, the diamine. So we take a diamine, an amine, simple amine. We make its amide using 3,5-dinitrobenzoyl chloride. And here the amide is formed. We take two R groups. One was the simple C16 chain, another was the O alkoxy chain on the benzene ring. The same length as that of the other one. So already one step gives you a long chain amide attached to these diamines. So these are the structure of the two diamines, and these are the physical constant, physical properties. One of the diamine was reported, the other was U1 or the Dover diamine. Third step was the synthesis of polymer. So we selected the oxythenic anhydride and we carried out the reaction and we did N-methyl pyrrolidine 0 degrees C 24 hours study. This is the polyamic acid which is formed by the opening of the through the attack of NH2 of the dianhydride. The second step is the immunization process, which forms this tetracyclic ring, the imide section. So these are the codes from these two diamines and the simple anhydride used here. The characterization. So this is the simple diamine, not much to give you for characterization. So what we see is the NH2s and NH of the amide linkage both are visible, and then the aryl hydrogens and the carbonyls of the amide at the usual places. This is the CHN of the two. So the CHN also correspond with the theoretical values. The NMR, so as you are in the iccbs, so you very well know the NMR. I will not elaborate it. So just the imidic NH is observed at is this place, and this is the here. So the very diagnostic NH2s are visible after 5. So 5 ppm, 5.06 ppm. The C13 also establishes the same structure. So imidic carbon is observable at this place, at this H2 here. FTIR, so polyimides. So these are the long molecules. So and their solubility matters a lot. For NMR, we know that we have to use the deuterated solvents, and these polyimides were not soluble in the deuterated solvents available to us. So we just took the FTIR. FTIR is very helpful to distinguish whether the polyimide is formed or not. The characteristic peaks which are which are there for the polyimide formation are the two carbonyls, one arising from the asymmetric stretching vibration at 1778 per centimeter asymmetric stretching, and the other is carbonyl stretching for the symmetric stretching at 1700. So once we get these two peaks, we are sure that the imide linkage is formed. Also, you see no NH present here. NH2s present here, which is also a very characteristic indication that the NH2s have been exhausted. Now, for a robust polyimide, we know that the thermal analysis is used. This is the thermogrametric analysis of the two polymers, and this is the DSC or differential scanning calorimetry of the two polymers. So you see that these are quite stable. So after 250 के बाद ये decompose होते हैं. So initial decomposition for one is 268. The initial decomposition temperature for the second one is 295. And these are the 5% weight loss temperature and 10% weight loss temperature. For the glass transition temperature, you see 152 for one and 155. So below this, the phase of the polymer is amorphous, above is the rubble. So you can work below this temperature, right? So approximately 140, you can safely work with these two polymers, and they do not degrade until and unless you increase the temperature above 300 degrees C. Solubility and viscosity. So if you have a polymer and you want to coat it, the polymer should be soluble in some solvent. You see here the solubility data shows us that in the DCM, chloroform, acetyl, methanol, they are not soluble. This is the usual characteristic of polymers. Then in DMF, they are soluble after heating. Same is with metacresol, DMSO. And the first one is soluble at room temperature in DMAC and NMP, while the second one is soluble in NMP at room temperature. So this window is the working window for us to play with this polymer. So coating के लिए we will use these two. We can use these two solvents. Also, the viscosity of polymers is important because it gives you an insight towards the molecular weight of the polymers. We used double Hort viscometer in the NMP solution, and we see that moderate viscosities are observed, which means that neither high molecular weight polymers are there nor very low molecular weight oligomers are there. So the polymers are formed with a medium range of molecular weight, around 40,000-50,000 gram per mole. Now about the fabrication of polymers stirred liquid crystal based sensors. So we used a solution of polyamide in DMAC, and we spin coated the solution on the glass plate. So this is the rotation spreading out under vacuum of the polymer sample. The solvent is evaporated, it is dried, and it is coated. So you see here the polyamide is coated on the glass plate. So glass has OH, and in the structure of polymer you see there are various electron donor and electron acceptor species. So there are carbonyls, there are nitrogens, wide linkages, NHs, they are present, so they can interact with the OH of the glass to form a very good coating on the glass slide. Then we put a temp grid on the slide, we deposit a liquid crystal which is doped with a liquid, and then we heat the liquid crystal above its transition liquid crystal to isotropic transition. So in isotropic state, liquid crystal molecules are randomly dispersed. So we annihilate, we heat it to a higher temperature in the isotropic phase, then we cool down it to the room temperature. And after heating, when we cool down all the liquid crystal, they then try to align themselves with the on this grid. And what we see, so if they are aligned homeotropically, we see some liquid crystal pattern under the polarized optical microscope. So once we have formed our sensor, we come towards the optimization of the condition with the liquid crystal sensor. So first thing which we need to do is the optimization of the concentration of liquids. How much amount of amphibolic liquid is to be put on the grid to give us a good optical image. So we see 0.8% of amphibolic liquid. You see the pattern or the texture is different. It is bright. When we add the ligand, it is slowly going to disturb the texture. Means the liquid crystal is now being perturbed by the presence of the amphibolic liquid. And here, 128%, it is showing the dark texture, the dark image. Means that homeotropic alignment is now being formed. You see here, you see the liquid crystals alignment. तो लिक्विड क्रिस्टल यहाँ पे अपनी अलाइनमेंट जो है वो शो कर रहा है, राइट. बट हियर यू सी द लिक्विड क्रिस्टल इज नॉट शोइंग एनीथिंग. इसका मतलब क्या है कि व्हेन यू विल ऐड सम फॉरेन ऑब्जेक्ट and it will, if it interacts at the liquid crystal interface, aqueous interface, it will show its signal. So if it interacts, it will change this thing, and if it will not interact, it will remain dark. So from here we see this is the optimized concentration for this amphibolic ligand. And in the case of the second amphibolic ligand containing the certain moiety, we see that 0.158% after this 8% of ligand, we are at the dark image. Okay, the dark texture is being obtained. So these are the optimum ligand concentrations, amphibolic ligand concentrations, which we need for the liquid crystal sensor to work or to sense. So without the ligand, the a bright optical texture was observed, increasing the concentration led to darker area, 0.28% of first and 0.158% in the second case is the optimized concentration. Okay. Now the stability of homeotropic alignment. So once we have reached on the homeotropic alignment, this homeotropic alignment should be stable over a span of time so that we can perform the next experiment, or we can check what happens when we add the analyte, right? So this homeotropic alignment, it should be stable for some time. So you see, we have observed this homeotropic alignment for more than 2 hours, and this is the result with the first amphibolic ligand. So you can see that the homeotropic alignment is same, constant at least for 2 hours, and even after that. तो इस 2 घंटे के टाइम में आप काम कर सकते हैं सेंसर के साथ. So once you prepare this sensor, you can work within 2 hours to sense your the foreign analyte solution. Now we are adding the metal ions. So metal ion detection with ligand 5, as we have seen that this sensor was specially designed for the mercury ion detection. So we added the highest concentration of mercury in the liquid crystal sensor. So 0.3 millimolar is very high concentration of the mercury. Not only mercury, we also added the other metal ions also to check whether it is selective only for mercury or it can interact with the other metal ions also. So these different 12 tests were done with different metal ions, same concentration. And at the same time, we took the visible spectra of these solutions. What is observed is that with the mercury kind, we observed some bright texture, with the others, no texture is observed. It is also evidenced here that with the mercury, we observe some shifting of the UV visible band, and the other metals, they give you almost same type of pattern. So both the results, they are in coherence with one another. With the second amphiphilic ligand, again the same testing was done. And here also we see that the mercury ions introduction in the liquid crystal sensor gave you bright texture, and in the UV it gave you a shift of the band from 466 to a maximum of 476 nanometers. So these changes, they show that some of the things are going to happen with the mercury and your ligand. Now, what is the mechanism? So, homeotropic alignment and detection methodology and liquid crystal aqueous interface. So, liquid crystal aqueous in the absence of the liquid, as I told you before, when you have only liquid crystal, you will only see the bright texture. When you add water and it aligns the molecule, the film become the liquid crystal sensor shows you the homeotropic alignment. So this bright image is going to the dark one. Now when you add some foreign object, two things can happen. Either it can react with this arrangement, interact with this arrangement, or it cannot. So if it does not interact with this arrangement, the same thing will be observed. So the dark image here, upon addition of something and a light for a body, again the same dark image is obtained. It means your analyte is not interacting with your system. It is not disturbing the molecules, liquid crystal molecule. If it interacts with it, it will disturb the arrangement of the liquid crystal molecule, and now they are not homeotropic. They are showing you the tilted alignment. So in different direction, the molecules are tilted. And what is happening from the dark texture, you are getting the bright image. आप देख रहे हैं तो again this is the liquid crystal is showing you the threads and bright colored texture in the liquid crystal. So it means that in the first case when the mercury interacts with this amphiphilic molecule, it changes it forms some complex with the amphiphilic molecule, and the liquid crystal arrangement is disturbed, and you get this type of response. Another thing for the sensors to be determined is the limit of detection. How much down it can detect your foreign body or your analyte. So with this amphiphilic molecule ligand, we check with different concentration of the ligand, and we see that the bright images are going to appear, and slightly, the birefringes is going to disappear, and they are going to disappear. Brightness is decreasing. So you see here, brightness is decreasing. And this is the benchmark value of luminescence. So below this, we cannot see, our eyes cannot see the luminosity. We cannot detect any change. So 30% luminosity should be obtained. 30% luminosity is obtained with 0.5 micromolar. So it means that we can detect 0.5 micromolar of the with the 0.5 micromolar of the solution of amphiphile ligand, you can detect some change. If you decrease further, the any change in this will not be detected by your eye. With the second one, you see again from 100 micromolar going down to 0.15 micromolar. This is the luminosity curve, and decreasing down, and you see that 0.25 micromolar you get some luminosity above 30, so 30%. So this is the limit of detection for amphiphilic ligand amphiphilic ligand 8, and for the previous one it was 0.5. So from here also you can see that this one is the most suitable than the first one. Then there is reusability of the polyimide coating. So we can make one experiment. So first alignment of liquid crystal on the polyimide coated glass slide and liquid crystal aligned. Then sample analysis were done. After the sample analysis, we washed this grid with the ethanol and then with water and acetone. We dried the glass slide and we use it again. So this is the second alignment. You see the dark image is the same as in the first one. It means the polyimide coating has not been changed or worn off. And when we used it for the third time, we see that now it is showing some bright texture. It means the polyimide is not in the same condition as it was in the previous one. So already with this experiment, you can use this liquid sensor twice. But we can optimize the conditions here and increase the reusability of the polyimide coating. Comparing with the literature, different doping molecules have been used as ligands and with different liquid interfaces and glass coatings. Here you see thiazole thiophenase ligand was used. LOD was 10 micromolar with amphiphylic dithiocarbamate. The LOD was 0.5 micromolar. And with our results, we see that the first one, polyimide, it gave you 0.5 micromolar level of detection, which is comparable to this one. And the thiazole was certain it gave you even lower LOD, 0.25 micromolar. So this is a good result. These are good results. They are compatible, and in this case, superior to those reported in the literature. We also performed some testing functional studies on this is the optimized geometries of the two ligands. It is the linear molecule. This is not much linear because we have a cyclic ring here and the other things. So these are the homolumo calculations, electron density distributions without mercuric ions and with mercury ions for the two ligands. For the HOMO, you see the electron density is located here in this case, while in this case it is located here with the sulfur and nitrogen. But in this case, on the benzene here. And when the mercuric ions are added, you see these two are changing. So all the electron density is now being concentrated on this part. And here also you see a lot of things being happened here. So this also constitutes an evidence that in the case of mercuric ions, you are actually disturbing the homolumo situations of these compounds, and something is happening with these parts, with these two parts. And these are the energies, calculation of energies, homolumo, and the band gaps, and the energies of the ligand mercury, and the binding energies. So the interaction energy calculated using these two equations show that the more negative value of binding energy is found for interaction of the compounds 8 with mercury ion than the 5. So same type of result as we have seen in the case of UV and in the case of polarized microscopic results. So the lower band gap obtained from DFT also shows that the compound is reactive in nature. Here you see the LUMO and HOMO calculation. So HOMO without the mercury ion is 5.174 and with mercury it has a high energy point. HOMO is more energy, so 9.9. And the band, the energy difference is 1.3, the least among the four. And the binding energy with the mercury ion is the highest of the two. It means that this complex is more stable. And you see the delta E binding is more in that as compared to the above case. So they have favorable interaction of the ligand with the mercury ions. So all these results are showing the same thing. So this is one of the dissemination of result, one of the first publication in chemistry select. This was the second one, and Polio International. Then we have also, do I have some more time, please? 2-3 minutes, Dr. Khalid? Can I talk 2-3 minutes more, or should I conclude it?
Yes, ma'am, you can.
Okay, so we also have done some work with the polyamides as adsorbents. So we made some sulfonated polyamides and used them as adsorbents for the detection of lead ions. So this is another work. So here we used the sulfonated diamines in the form of their salts. We polymerized them with the dihydrides with another amines. These are the copolymers. And this is the polyamic acid stage, the polyamide stage. And here you see we have used different X atoms here and Y atoms here. So Y is 3, 4, 5, 6 amines and 2 of the anhydrides. So why we change only 2 anhydrides? Because they give us a flexible coating. The polyamides can be coated with these 2 anhydrides. And here also you see the oxygenated functionalities are there. So we are designing different types of polyamides to form its coated films. So these are the AAS terminal absorption spectroscopy result with the two different anhydrides where we see with the oxygenated oxidized anhydride we get the most adsorbent most of the lectins were absorbed as compared to the other ones. These were some of the calculations for the pseudo first order and second order rate equations. And here also we performed some theoretical studies for the oxy and fluorinated dihydrides. So here you see with the oxygen containing the dihydride, you get the electron energy which are poor in negative, which means that these separated polyamides, they made good bonding with the lead too. So most of the lead can be taken out from the water with this dihydride as compared to the other. So in conclusion, the overall results that we are the polyamides, they are innovative materials. And this lecture, what we have shown you is the first ever use of polyamide coating for liquid crystal based sensors, optical sensors, and we have showed that it has a good selectivity, exceptional selectivity for mercury ion detection, and they are sustainable also. We can use it again, and they are highly thermostable. Acknowledgement, first of all, Almighty Allah for giving me strength to cross all the boundaries and to work in all the national and international environment. Prayers to my parents also, which stood with me in this journey. Department of Chemistry, Ghazi University, which gave me the platform to do my work. Higher Education Commission for the funding of the various projects. And my 3 students, PhD, ex-PhD student, Dr. Asma, Dr. Alia Nasir Sahab, Dr. Nasir. So these are some of the students in our group. Thank you very much. If you have any questions, you are very much welcome. Thank you.
Thank you, Professor Humaira Masood. Thank you for such a wonderful and informative talk. Now this session is open for questions. Please. So I don't, am I audible? You can मेरी आवाज आ रही है मैडम
जी
आपको?
जी 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 डॉक्टर खालिद, आपकी जरा क्लियर आ रही है, आप
आप
बता
यहाँ
दो।
है करीब आए।
जी, so what's the question?
Sorry for the inconvenience.
करीब आ जाए।
Madam, ये जो
जी
I am shocked as a chemist and I am curious as a chemist. आपकी जो कंपाउंड 8 और कंपाउंड 5 था उसमें सल्फर था, उसके जो हेड था, बाकी एम्फिलिक पार्ट भी था। तो हेड में मरकरी का जो है ना, आपने एब्जॉर्प्शन, वो बाइंडिंग एनर्जी भी आपने दिखाई, एक ही माइनस में आ रही थी, -1.5, विच इज मोर एनफ देन फॉर सिंपल सेंसिंग। ये तो अच्छा है कि उससे रिमूवल किया जाए मरकरी का, और दूसरे का पॉजिटिव आ रहा था। सो हाउ
जी
इट इज पॉसिबल? और ये दूसरी स्टडी में आपने एमओई से जो है ना, प्लम्बम की जो है ना वो एग्जैक्ट एनर्जी दिखाई है। तो एमओई से तो सेमी एम्पिरिकल मेथड है, और मतलब मोस्टली अगर उससे हम जो है ना एग्जैक्ट एनर्जी निकालेंगे तो मोस्ट चांसेस यही है कि वो गलत होगी ऑलमोस्ट। तो एब इनिशियो मेथड उसके लिए क्यों यूज नहीं किया है, जो दूसरा आपने स्टडी दिखाई है? थैंक यू मैडम।
अच्छा, थैंक यू। हाँ, एक्चुअली ये स्टडीज जो है ये मैं खुद नहीं करती, मैंने किसी और से करवाई है, कोलैबोरेटर से। तो उस वक्त जो हमारे पास सिर्फ एक ही वो जो है ना एमओई वो हमारे पास अवेलेबल था, दूसरा एब इनिशियो मेथड हमारे पास था नहीं। तो इसलिए हमने उस वक्त जो है ना वो यही की थी, बट इट्स अ गुड सजेशन कि वी कैन आल्सो get a good response if we apply the same results। हम उसको दोबारा से जो है वो आप जैसे बता रहे हैं बेनिशियो मेथड से भी कर सकते हैं।
मैडम,
the
और
other
ये यस, कंपाउंड 8 की जो बाइंडिंग एनर्जी है वो पॉजिटिव आई है, तो हाउ वो सेंसिंग कैसे कर रहा है या वो डिटेक्शन कैसे कर रहा
ये कौन से वाले में बता रहे हैं आप?
है? 5 और 8 जो आपने उस
पहले वाले में, हाँ जी।
दिस वन कंपाउंड
नहीं,
8 मरकरी
मे बी यहाँ पे ये वाले ये -1.55 है, ये टू
माइनस वन
पॉइंट
पॉइंट फाइव भी काफी ज्यादा है, मतलब ये तो डिटेक्शन के लिए अगर हम कहेंगे तो इतना वो नहीं है, लेकिन ये दूसरा वाला तो पॉजिटिव आ रहा है, तो ये बाइंड ही नहीं हो रहा, इसका मतलब है तो डिटेक्शन कैसे कर रहा
नहीं, मे बी यहाँ ये माइनस है, -2 पॉइंट, सॉरी यहाँ पे गलती है, ये माइनस है, ये
है?
-2
ओके,
पॉइंट। हाँ जी, थैंक यू।
लेकिन ये
थैंक यू
भी
फॉर
कभी
पॉइंटिंग।
ज्यादा है इन इलेक्ट्रॉन वोल्ट,
जी,
मतलब इस मटेरियल को
तो
हम
इसको
रिमूवल
हम
के लिए यूज
नहीं
कर
नहीं,
सकते
रिमूवल
हैं।
नहीं, अभी हम सिर्फ डिटेक्शन के लिए कर रहे हैं। ठीक है, इसको ये हमारा फर्स्ट एवर जो है ना वो अटेम्प्ट है, जिसमें हमने फर्स्ट टाइम ये जो है ना पॉलीमाइड यूज करके इसको डिटेक्ट करने की कोशिश की है। आपको पता है मरकरी को और भी बहुत सारे सेंसर्स जो है वो करते हैं, ठीक है ना। हमारा इसमें जो पार्ट था वो था कि हम पॉलीमाइड बेस इसके साथ जो है ना उसकी कोटिंग करके उसके ऊपर देखें कि ये कैसा रिएक्ट करता है। तो ये दीज आर वेरी फर्स्ट रिजल्ट्स, ठीक है। वी विल ऑप्टिमाइज देम, क्योंकि मैंने अभी आपको दिखाया कि सिर्फ ये पहली हमारी वो है अटेम्प्ट है, इसके बाद हम इसको मजीद जो है वो आगे लेके चलेंगे।
थैंक यू मैडम। आई हैव ए क्वेश्चन। मैम, आपने एक स्लाइड में बताया था कि ये मॉलिक्यूल्स हम वायरसेस की डिटेक्शन के लिए यूज करते हैं। तो
जी, ये वाले नहीं, मेरा मतलब था कि हम और काफी सारे जो है ना हम एनालाइट्स के लिए यूज कर सकते हैं लिक्विड क्रिस्टल्स को। वो और तरह
ओ,
के, वो हमारा सिस्टम नहीं है। वो मैं इन जनरल आपको बता रही थी कि लिक्विड क्रिस्टल सेंसर और कहाँ कहाँ यूज हो सकते हैं। उसकी मैंने आपको शायद वो नहीं दिया कोई रेफरेंस, वो हमारा सिस्टम नहीं है।
ओके, थैंक यू मैम।
जी,
कोई और क्वेश्चन? So if there is no question, we will close this session. We will reach you, madam, for more such wonderful full lectures in future. Thank you, madam, for
थैंक यू
accepting
डॉक्टर
our
फॉर
invitation.
encouraging। थैंक यू ऑल द स्टूडेंट्स एंड ऑडियंस, अल्लाह हाफिज।
Thank you, ma'am. Thank you.